Okay, more Goonies. So we were looking at the algorithm here that decodes the room data. And so we had a couple conditions here. The 10, 20, 30 thing we saw in the code. I'll have to look that up again in the assembly because I can't remember exactly where that was. So let's get the assembly in Visual Studio Code here. And then, I mean, it's not going to be as easy as finding OX30, I guess. Well, no, of course not. Actually, that was a compare, I think. I don't know how many spaces are going to be between that. Also, I don't know the register, so can't really do that, but that's fine. Let's see, how do we go back? So yeah, the data was at least stored at these locations, so we do know that. I'll get a watch point on that address again. It's going to be a read memory, of course, and we'll see if it gets accessed. Yes, it should. Yeah, it is now. Oh yeah, we had a couple of functions as well. So let me open the symbol file. That's still in the old folder. I did rearrange some stuff here, but the symbol file is still here, which is okay. Yeah, the functions are at the bottom here. All right, so we have a decode level data pointer chunk, and then the temp buffer. Yeah, we have to keep track of all those guys. Right, because if you look at the code here, we were looking at a very specific thing. Let me get some a window open for executing our code here. Oops. And then we are in MSX Goonies, and I have to specify the ROM now. Okay, so yeah, so we have a top nibble of OX30, and then we're falling through. So we're interested in the falling through part of it. So that's these if clauses here, right? I mean, it should be else if here because I mean I should look at this function in the code though. But I'm considering we have a falling through here, this thing here. That implies that we should fall through 10 and 20 hex too, though. But yeah, let me find that part again in the code here. Let's see if I can find it from the sim file. Maybe it's one of these for FE8. That's a bit below this, but let's scroll automatically. For FE8 is reset working area, right, on room load. Well, that's not going to be it, right? Decode level data pointer chunk. So that decodes a chunk of 8x4 tiles of the current room. Yeah, I think it's that, right? 59E7. 59E7. Where are my? Oh yeah, no, here they are. Well, yeah, 10, 20, 30. Okay, so the function we're looking at is decode level data at 5A05. Yeah, okay, it was the next one. So this is the temp buffer. Yeah, okay. We're still decoding into the temp buffer. And that, yeah, because the temp buffer gets copied into the output buffer the exact same way every time, right? So the write temp buffer to output buffer is just a mapping of the 4 lines on top of each other. That's true. So what we're doing here is indeed decoding the temp buffer. I mean, I could have looked at the function name here, but that's fine. Okay, so we're following through these if clauses here, right? So we're comparing with 10 hex, 20 hex, and 30 hex, and so we're jumping to 5A43 in case of 30. So that's this chunk of code here. But if we don't match either 10, 20, or 30, then we do what happens in this thing here, meaning that considering all these other clauses, these other conditions, I mean, also jump away. So 5A32, 5A29, yeah, so they are indeed else ifs. We only do it, we only do one thing based on the top nibble of the byte here. So yeah, those have to be else ifs. And what is this? Yeah, so we're checking whether it's 0. I don't think we're doing this comparison in the code yet. Yeah, and we're comparing with E2 hex as well, so I don't know exactly what that was about. So we'll have to look at that again. But for now, let's go back to the fall through. So not this jump. So the case where we don't take this jump, we end up loading the value of DE into A, and that should be the thing where we ended up. So DE is presumably the temp buffer pointer, and we are writing the byte simply to the output or the temp buffer, and we're loading the. Okay, I'll have to look at the registers here because they're both being loaded. Well, no, we're reading from DE and we're writing into HL. Okay, and then we're increasing both, and we're jumping to 5A08, which is all the way back up to the function, and we're handling the next byte, meaning that fall through just copies 1 byte, and that's it. So let me look at the execution here again. So we're writing E0 at our location. So this first block of code is like the first 4 columns of 4 rows, and those are all the same. Of course, I didn't have this executed now. I skipped this at the bottom here. You can see if I'm doing my YX looping, I'm starting at Y1. That's why it skips over the top part here, although it does write stuff out though, so that might not be correct. Because what I wanted to do is to skip the top row. We've already decoded those, right? So let me see. So I'm going from I'm doing 0 and 1 for the Y, and X is also the first column from 0. So let me do all 4 here. So from 0, 1, 2, 3. So if I do that, then the top part should be filled in. But I think with how it was, the top part should be empty though. Right, but that's because I haven't, yeah, I'm missing stuff still. So let's execute this. Right, so now if we do all the things, that means that, oh, no, okay, sure. We do decode the top 4 columns as well, right? Which renders these 5E5Fs. That's why I disabled that. Right, so that's an interesting one as well. So wait, where are we? So 1, 2, 3, 4. Okay. So those are the 4 columns of the top row of the top section. And then we start with the one we're interested in. Right, so we're writing E0, but I think it gets overwritten here because I think the E0 should be here. But one of the other algorithms is taking over. So let's go back to only doing this one here. And that means that's on Y1. And yeah, below 2, that's fine. So that only gets executed once. And then X is going to be 0, but we're only and we're only doing it once here as well. So we're doing the second row, first column. Right, so that's our temp buffer. I think that's incorrect. Oh, no. Yeah, we're doing an OX30 first, so the E0 has to be here indeed. So we're starting from this one. Yeah, so it was indeed correct. So the first 4 columns of the top row are here, and then the next ones are here. So we are writing E0 and E1 in those positions, and that's the fall through, and that should be enough. So what I'm thinking now is that the next problem is not going to be the fall through, but one of these guys. The 10 and the 20 might be hit. So what I want to do is I want to see what the temp buffer looks like in game when we reach this point. And I think, well, I have to go through, yeah, so if it renders the first 4 columns of the top row, it's always going to be OX30, right? Because we hadn't encountered that yet. And then the first thing it's going to do is going to hit the fall through. So I just have to put my breakpoint on the fall through, which is right here. Yeah. Where are we now? Going to disable this one, 5823. So let's just run to this point, right? Yeah. So in principle, we should be at the exact, or at the start of the exact same positions we are here, meaning this one shouldn't be filled in yet. Oh, there are 80 guys here too. That might not be correct. So let's look at the temp buffer. I think it should be only filled with hex 80s at this point. And the rest should be empty. So now we have to figure out again where the temp buffer is. I think I did make a symbol for that though. I might not have. It was 6E00 was the output data, I think, if I remember correctly. And then above that, or was it? No, it was E6. Yeah. And then above that was the temp buffer. Yeah, this is the temp buffer. Yeah, temp area for level decoding. Right. So we do have the data here. So we're seeing completely wrong stuff now, although it's keeping the stuff from the row before that. So the 5F, 5E stuff, that's just simply from the row before. That hasn't been overwritten yet. But this is completely wrong. So we are writing 80s hex, and the game is writing E34D for EEC3 for some reason. Right, what we then figured out was that was the ceiling adornments where the stalactites are. Yeah, that was that. Right. So I don't know why I'm doing this wrong, but the question is, are we writing E0 and E1 at this point? And it doesn't really look like it's going to do that, but let's take a look anyway. So we're in the fall through. We are pointing at E1F8. That's indeed the first byte here. And the source is 5D5F. So let me get a different window open here. So 5D5F. Right. Although, no, 5, okay, I was looking at this one. No, it's over here. So yeah, we have 3280, which appears to, oh, no, the 1 was the problem, right. We had 30 and 31 last time. The 0 meant alternate between +1 and -1, or +1, 0, +1, 0. And the 31 was the other way around, like minus, right? 30, 29, or 2F, etc. Well, I mean, it's actually the value byte that gets added and subtracted from. So yeah, I think we left off at that. So we are pointing to 5D5F. Yeah, so we are in the value byte here. So I'm assuming it's going to put my 5E that we're talking about here in this first position, right? That's all it should do. Yeah, so it wrote it in the first position here, and we're incrementing both, and we're jumping back up to the next byte, which then becomes 07E1 here. So that's going to be the hex 10 thing, maybe. Let's see. So it's not this comparison. Oh, we jump to 5812. Okay, so yeah, we're skipping stuff here. that's fine. I think we've always done that though, that's fine. Right, and then we're doing our comparison of the top nibble, which in this case is 0. Okay, so that's the other case. Okay, so now we are in this position. Yeah, it's this guy here. So it can be 0, hex 10, or match with hex 10, 20, 30, and fall through. However, instead of going forward with the next byte, I have to know why these are different from my result. And that's the 3280 thing. Yeah, so we definitely have to look into that. So that's because of this 5D5F. Yeah, it's this 32 here does something different. So that means that makes it a bit more difficult unless we're doing a read watch point on this byte. Yeah, I'm going to do that because I need to pause the game at the exact moment this is being handled. So let's make it easy on ourselves and put a watch point, a read watch point on this byte, and let's reload the level. It is reading this one later on though, that's not correct. Why is it reading from that one over and over? So DE is pointing to 5D5. Is it tracking back? That's weird. Or is it the wrong 3280 that I got here? Well, I mean, it shouldn't be, right? 5D5D is indeed our byte here. Yeah, it's hitting that multiple times. Oh, but that can be because... Oh yeah, it's probably doing that 4 times because these 4 sections may be repeated. Yeah, actually, if you look, you have 11211 112 so ignoring this stalactite here, 112 112 and then that one is cut off. So yeah, it looks like these this column here, there are 4 columns, right? They are handled per 4. They are repeated. So these adornments on the ceiling are repeated 4 times. They're identical, right? Meaning that this position would have been loaded 4 times. What I'm thinking now is if they store the level data like that, it's going to make it hard, if not impossible, to like overwrite our own set of data for the rounds here. That would make it a bit difficult. But I mean, fine, I guess. Then we can just extract. Okay, so let me restart. Okay, my thing isn't working. Okay, now it is. Okay, so the first time it hits now, it should be in row 1, as in 0 and then 1, and then the leftmost column. Okay, so we're pointing at 5D for the first time, right? So that's the 3280. And what we do here, so we're taking the top nibble, which is 30 hex. So we're gonna fall in this clause here, but we're doing something different though, which is not something we've done before. So yeah, we're taking the top nibble. It's not 0. We're comparing with 10. Oh no, it's 30. It's 30. I was okay. Yeah. It's this jump. It's this jump. Yeah. So 5A43 is our routine. Okay. So now we're in the code here that handles this part, right? So 5A43. I'm going to look at it on the big thing here. Right, so that's only being called once. Okay, and it should, well, we have an unconditional jump here. Okay, yeah, sure. So that's the last thing here. Oh, and we're calling a function. So we're pushing DE here. That's the 32 value pointed to by DE. And we're calling 5A50. We're dropping and we're incrementing twice, meaning we go beyond the value byte, right? Because it now points to the 32, and after that was the 80, I think it was. Yeah. So this 80 here is being jumped over, I guess. So we're pushing and popping here. to traverse to the E0. That makes sense, but the bulk of the thing is in 5A50, which is right here. And there are conditional jumps. Yeah, we've seen this before, and it runs until here. So something in this code handles the fact that the bottom nibble is 2 instead of 0 and 1, which we encountered before. That's, yeah, this here. Yeah. So we were here, right? We were handling the fact that the bottom nibble is neither 0 or 1. Okay, so we will see where that ends up. Let's first take the jump to 5A50. I'm going to have to go in this function, 5A50. Okay, and then we're loading DE again. That should be 32 into the accumulator. Yep, that's 32. And we're going to the next byte. So we're pointing already to the 80 hex now in DE by incrementing DE. Yep. And then we're taking the bottom nibble. Okay, that's not, in case it's 0. So that's this one. Right. So that doesn't happen. And we are decrementing the bottom nibble. Okay. Sure. And we're checking again if it's 0. So this might not be the best here to do an else if, because we have to do something after this, right? So if it was 0, in the case of 30, we would have jumped to 5B29. Okay, that's far away, 5B29. And what we would have done was load the value which would be the 80 hex. We would load it into C, we would increment 80 to 81, and jumping back to 5B31. I don't know, we're jumping forward to 5B. Oh yeah, and then we write it out. Okay. Wait, do we write out the same byte 4 times? That would not match with what we're seeing here. So we're writing the byte out 2 times. Oh yeah, no, it's we're switching between bytes, right? Okay, so yeah, that's the increment option that we had here, right? If it's 0, and that does make sense. But what we're actually seeing in the code now, so where we jump to 5B29, that was in case it was 0, and then we decrement, and again we check for 0. That was the one case, and that's going to be, so 5B2E is going to be the minus variant. 5B2E, yeah, that's the decrement, right? And then we write out the 4 values. But we end up here, right. So this actually should be bottom nibble decrement, and then we check again whether it's 0, and then now we are handling the case where it is, in case it was 2 at the start, we decrement twice, so we end up with 1, not 0, right? And then we end up in this section here. So we are decrementing again, I think. Wait, so this is the check for 0, this is the check for 1, and we do decrement again. So it's 1, and we decrement, so it wasn't 1 or 0 yet. Then we decrement again. Okay, so we do that again. Okay, and now we're going to do stuff. Oh yeah, this was the array that contained the adornments, right? Actually, I can just do 1 and 2 here. No, well, 0 and 1 here, because that's always going to be the case, right? So we don't have to rewrite it with the bottom nibble here. Question is the fall through of this always going to, is it always going to be 32, or can it be 33 or 4 or something like that as well? That's the question. I guess we'll figure that out when we encounter that data. I mean, I can actually do, wait, let me undo this. Yeah, I mean, that does make sense to do it like this, because it's the exact same thing, right? Okay. And then that's why I wrote here maybe needed bottom nibble -2, which is the 2 decrements from before. Now I remember. Okay, sure. Yeah, that's this decrement here. So we're loading A into B, which could be a counter, right? Because let's see. Oh, no, we're loading the hard-coded value of 8 into B, which becomes the counter for this jump here. Yeah, so it's not going to be an embedded counter or iteration count, I guess, for the thing, but fine. So we're loading A into B, and we're loading the value of DE into A, which is the 80 hex. Yeah, so we're saving this maybe needed value for sure. Then we're loading DE, which points now to 55E, which is 80 hex. That's this byte after the 32 here, this one here. Yep, and then yep, we're loading that into the accumulator, and we're storing that as well. And then we have our hard-coded pointer to 5A79. We've looked at this last stream at the end. This was the data for the adornments, I think. So if you go look at 5A79, and we're indexing in that array as well. 5A79 is this one here. But as you can see, so we're loading B again. That's, oh yeah, that was the index. So 32 means index 0 because we, yeah, okay. So that is, that's an array index. Okay, we'll temporarily name it like that. And then we have to look at, where did I do my offsets? Yeah. Yeah, we need an offset like this. So I don't know what this exactly is going to contain. I'm going to call it ceiling adornments now, but I'm thinking it's going to contain other stuff as well. That has nothing to do with the ceiling. I'm pretty sure that's just a general storage of like predefined sets of 8 tile IDs. But for now, let's call it ceiling adornments. So we are pointing to 5A79 as in the code here, right? 5A79 minus the ROM mapping offset, of course, right? So we have our ceiling adornments here, which we can now index into. Yeah, we're here, and that would be this guy here. But we're doing something. So we're doing a couple multiplications because they are sets of like 8 bytes, I'm assuming, because we're doing doubling. So we're doubling this 4 times. So for example, I mean, just to calculate it out, I mean, it's very easy, of course, but in our case, we're in 0, right? So it remains 0. But if we have 5, index 5, and we're doing times 2, times 2, times 2, times 2, then we are at 50. Of course, I'm in hexadecimal. That doesn't make sense. That's 80, and that would make, would that make sense? No, that's 40, right? Why am I? Uh, 10, 20, 40, 80. Yeah, that is correct, of course, obviously. But if I index it by 8, then we are in position 10, though. Would that make sense? I mean, it could be. If we're, is that always a double? Let's see. So that's of course 64 over 8 equals 8. Yeah, so 4 becomes 8. So it's half of the index then. I mean, that's exactly what's happening though, and it is copying 8 bytes, right? So I would have assumed that. Wait, so 1 times 2 times 2 times 2 times 2 is 16. So we're skipping 16 bytes, right? That would put us at index 2, and that which is the third, right? Because we have 0, 1, and 2 as indexes of bits of 8 chunks of 8 bytes. I mean, not that it really matters, right? But it's just it's pretty much this. So the index times 2 times 2 times 2 times 2. So that's our pointer. What are you complaining about, size t? Our index equals bottom nibble minus 2. That should be a uint at. Oh, right. I need to read it from the ROM, of course. Yeah, I don't know what I call this ROM data. It's this plus this, right? We have to actually read it from the ROM, obviously. I'm still complaining. Right, I need to get the address of that, I guess, because, just to make sure, let's put some brackets around that. Why are you still complaining? Unused variable, okay, that's fine. Yeah, so we're pointing to that now. I mean, actually, I can just iterate and add from 0 to 7, of course, that's also possible. But yeah, what we're doing is we're loading that base pointer, and we're indexing b, which is the bottom nibble, minus 2. And then we're adding that to that pointer. That makes sense, because that's pointing to, wait, let's see. Yeah, oh no, yeah, that's 5A79. We're adding that, and then we're looping from here to here. Okay, and then we're doing some rotations. Right. Now it gets interesting, because we're still dealing with, oh no, we're dealing with these guys here, right? Not with 80 hex. So I wonder where the 80 is going to come into play, because we did save that to the C register here. Okay, and it's being rotated left by C. Okay, so the 80 hex is what influences the rotation here of the bytes that are contained within this array. Okay. So we are doing, wait, let's call this simply a base index, and let's call this, so we have a base index, and this is where we start, and we do, our index is of course bottom nibble minus 2. Okay, so, and then now we can loop 8 times, right? Are we iterating I already? Yes, we are. So let's do a J. Also, we shouldn't be doing this, because that is part of these two guys. So I'm gonna take that away for now and duplicate it, even though that's not the best. But yeah, we're already copying 8 bytes here into the temp buffer, so we shouldn't do that routine for the minus and with the deltas here. No. So we have a base index, and now we can just loop 8 times and start copying and rotating And so the data is as base index plus j. So now we're looping the 8 bytes in that special array here at the correct index. And what do we do with this value here? So we're loading the counter, we're loading the value. DE is pointing to that specific value within the... No, DE, wait, where am I here? Okay, so let's continue with the thing so I can read the values better. So that remains 0, right? We're at position 0 because we're at 32. And then, yeah, so DE doesn't change, so we're still pointing to index 0 at 5A79. And then we're loading our counter for our loop. And then, okay, so DE is indeed pointing to the first byte here. So we are looping those bytes. And going to the next one, that's fine. And then we're rotating left with C. And where do we have C? That's this guy here. Actually, we shouldn't increment every time, of course. We're probably gonna do that. Yeah, I think that... Yeah, that has to happen somewhere else, so I'm not going to increment it yet. So that's our source bytes of, and then that's the rotation value, so to say. And we do have to increment that thing first because we're still pointing to... Wait, is it level? No, it's not level data index. I'm wrong here. Or not? Oh, is it? It's not meta. It's the same. Yeah. It's okay. So we did increment here by loading the meta byte, which is bottom nibble, right? Yeah. So we do have to get the next one. I'm assuming it's not going. I assuming we can increment here, and we're only gonna query this value once, right? We don't. So we use it to rotate left here, but we're not like it's in the C variable or register. So we're not gonna increment that yet here. So it's pretty safe to say that we can move on to the next byte for the next iteration of the entire loop. So we're gonna have to do a rotate left. I'm gonna have to cheat here and look how I did that. Where again did I did that? Where did I do that? I think it was in asset decoding. That's weird. I thought I did that in Eggerland here. Yeah, that's gonna have quite a bit of results. Of course, that's the one for outputs as well. Yeah, it's this one. This is a rotate right. Wait, so we're going to go 1 to the right, and that one goes 7 to the left. So it's the inverse of this, I think. Okay, and we are checking the carry flag. If it's not set, we jump to 5A73. So we're skipping these, well, or this instruction. We're loading what DE is pointing to again. Oh no, we are increasing the DE pointer here. So does that mean then that our data, I don't remember what the address, well, 5A78, oh no, that's the bytes, right? That's the bytes in the adornment thing. 5A7A. Yeah, that's those guys. It's not the data byte. So if the carry flag is not set, we do not do this. So if it is set, we are loading the current byte and we're increasing. Okay, so we're either rotating, or if the carry flag is set, then we're loading the byte itself. Okay, that's going to be a bit difficult, but sure. And then so we're loading that into HL, which is E1, which is our target thing here, right? E1 F0. Yeah, that makes sense. And then we're increasing HL to the next byte, and then we're ending the loop. So it all boils down to getting this rotate right, this rotate left correct, and then that should be it. Okay, let's see if I can do that. So I think this is a rotate right, and it's so wait, the value that's being rotated is C, which was our 80 hex, right? Yeah, that's this guy here. And what do we do with that? So it's 80 hex, meaning only the top bit is set. Does that have an effect on the accumulator? Let's see. I have to look up the rotation thing again in the opcode table. So the contents of C are rotated left 1 bit. The contents of bit 7 are copied to the carry flag. And the previous contents of the carry flag are copied to bit 0. Okay, so bits are 0 based. So it's the top bit is set. Yeah, that's what it boils down to, right? It just checks whether the top bit is set, because the top bit is going to be copied into the carry flag, and that's what's being checked here in this conditional jump. So for 80 hex, that top bit is set, so bit 7 is definitely set, which gets moved into the copy bit. In the carry flag, and then that, based on that, this load is being done. So if that load means it's reloading, okay, so it's doing a +1 -1 again, I think. So over here we're loading the value into the accumulator, and we're increasing DE. Okay. So we're loading the value, the current value, in our 8 adornment bytes. We're moving to the next byte, that's fine. We're checking whether the top bit is set, which is the case in our 80 hex. So we are loading the next byte, because we already incremented, into A. So we're skipping a byte. And then we're going again to the next one. But then we're exceeding our 8 bytes though. Oh, so is it an array of sets of 16 bytes then? Because that would make sense with my doubling 4 times. So if you calculated index 1, so 1 times 2 times 2 times 2, it was like 16, right? And then I divided by 8 to find out what the index was actually of a set of an array of 8-byte sets. But yeah, it was 16. And it would make sense, right? Because we're incrementing twice here, potentially. Okay, so I'm not going to do the rotation. I'm going to just check, because it rotates left. It merely checks whether the top bit is set, right? We're rotating left 1 bit. The top bit gets put into the carry flag. And we're only checking whether the carry flag is set. And if it is not set, then we jump over this line, right? Oh, is this an odd even thing? Why would you waste a byte on that though? Like an entire byte wasted on... It could be an odd even thing. So we have a set of 16 bytes, and we're either taking the odd every other byte either starting from the odd position or the odd or the even position, right? So let's see if it's correct, right? If my reasoning here is correct. So I'm not going to do the rotation. I'm just going to check whether no, 80 hex, so the top bit only equals or if it is set, I guess. And if that's the case, then we load the okay, so we have to do that. We have to do that manually here. Okay, so yeah, I can't use J. We have to loop 8 times, but I have to do our adornment index as a separate value. So we start at 0, right? Because that's our adornment index, which we increment. That's this increment here, right? And then we check. And if it is set, then the source adornment byte equals. No, I'm gonna do this separately. And then I'm gonna say this. So we're reading it again, but because we increment here, it's going to be a different byte, right? And then otherwise that doesn't happen, right? And then we just write it out. Okay. So now we write to our temp buffer at temp buffer index ++ equals source adornment byte. Yeah, that I think should be it. It might be the other way around, but I don't think so. Yeah, that has to have parentheses. But yeah, that should, I think, do what that says in the code. Okay, let's see if that crashes. So we end up with E3-4D, and there's a 0 here. I don't think there was a 0 here. Okay, that's not done yet. Should I loop through it or what here? So let's look at the other table first. No, not you. So we're starting at E3-4D 00 for E53. Okay, that's an identical copy though. So the top bit is set, meaning we're not doing, no, we are doing this. That doesn't make sense. Oh wait, I have to increment here as well. I think I forgot to increment. Yeah, so it's this, I forgot this one. I think it's like that, right? So increment once, and if it is set, we read the second byte, otherwise, yeah, I think it's like this. Okay, so now we have E3, okay, that's a bit weird. Okay, let's see what the game does. Yeah, so what's our state here? So we're gonna rotate left. Yeah, we're checking the top bit, right? So hex 80 was our input for C here. Yes, hex 80. And we're gonna look at the carry flag. That is going to be set because if we rotate to the left hex 80 one time, then the top bit is going to become the carry flag. So that should be, yep, that should be set. And we don't take the jump, so we are reading again, and now we are reading 5A7A, which is the next one. So 4D, and we're writing that, yeah, so we're reading the 4D into the accumulator. Oh no, wait. How is that possible? Oh yeah, no, wait. Didn't we increase? DE is 5A7A. Did I miss here? Did we start at what did we start? 5A79. 5A79. Oh, am I that far in? Oh yeah, sorry, we started at 5A79 and now we're at 5. Okay, so that was the E5 we skipped. Yeah, sure. So and we are using the second bit, the second byte. Okay, and we're incrementing again. And now we're loading the E3 into the first thing here. So did I get an E3 at the start? Yes, I do have an E3 as well. Okay, let's look at the next one now. And okay, so we're doing this 8 times, right? So our B register contains 8, which becomes 7 now. And then we're loading the next byte. So we're now pointing to the 4D here. We're going to load that one. And we're again going to take the next byte, right? We should, because the 80 hex hasn't changed, right? So we're going to increment or increase, increment the pointer to 7C. So now we're pointing here, which is for the next one. Okay, so again, the rotate left of hex 8, wait. C changed. Because C is now 0. Where did that happen? Okay, that is different. So I'm misunderstanding the rotate left here. Oh, right. So the contents of C are rotated left 1 bit position. The contents of bit 7 are copied to the carry flag, and the previous contents of the carry flag are copied to bit 0. Okay, so C does change. Okay, right. So I can't just do no, not you. I need this. Yeah, I can't just do this. I do need to. So it's doing this once every 8 bytes. Then that's such a weird thing, right? Because the moving of the top bit into the carry flag only happens once if you keep rotating left the same bit 8 times, right? Of course, if you have a different value than hex 80, in other words, a different value than just having the top bit set, then that might change, right? So we do need to rotate left, I guess. Okay, so let's keep a carry boolean here, and I'm going to start that as false, so in other words 0, and I'm going to, no, I can't do that. So if we rotate left, so let's start with shifting left, right? So if the top bit is set, I can set the carry to false, and that becomes 1. And actually, I'm not going to use bools just to make sure we don't make a mistake here. So I'm going to use 0 and 1. So if the top bit is set of the rotation value, then that would set the carry, and then we just shift it by 7 bits, right? Is that correct? Or shift it? No, we're shifting 1 time. No, we're only shifting once. And I need to know whether the carry was 1 at the time, because I have to add that now. So I'm going to say and then I will say like it's this plus the because now I have to add this previous value, which is 1 or 0 to the rotation value. And then the consequence of that is if the carry bit is set, which is then, I mean, I'm going to do this, then we reload the bytes. Is that correct? Okay, what is it complaining about? Okay, that's a casting thing, that's fine. From into uint 80. I mean, I'm dealing with uint 80s here, so why are you complaining? Oh, is it this one? No. And that's such nonsense. I'm not I'm still complaining. I'm not converting anything though. Previous carry is like, I mean, I didn't explicitly say it's a thing, event AT, but like there's no int in play. Like, is the result considered an int? That's a bit weird though. Yeah, apparently it sees the result of this addition as an integer instead of keeping the same type of the two things. But that's fine, I guess. Yeah, so the shifting would get rid of the top bit, right? So let's see if that gives us any other results here. It does not. Was that to be expected though? Oh, right, because, yeah, are we doing this? That's the question. Are we making the difference here? In other words, let me verify that. Yeah, so and what I want to do is, does this work? I actually don't know if format has a binary formatter. Apparently it does. You should do 08 though. Okay, that doesn't look correct. So we're starting at this, right? That's 80 hex. And then the 1 gets put into the carry flag. The carry flag is 0 at the time, so that becomes 0. So that's good. Then the carry flag is 1. Okay, let me put, instead of guessing here, right. Okay, so the carry remains 1. Okay, sure. That's incorrect, of course. That should be conditional on the entire thing, right? 1 or 0. Yeah, so the carry flag is dependent on the top bit being set or not. Okay, so indeed the carry flag is here. Now the 1 just shifts over neatly. That's correct, I think, right? So we start with 80 hex, then it becomes all 0. Yeah, but the carry was 1. Okay, so we have different values here now. That also looks good, because I think that's correct. I think that's what we are expecting to see. Yeah, so let's continue here in the game. I should have made a screenshot of how it looked like when it's finished, because now I have to run through this thing. So yeah, now we are making the jump because the carry flag was not set. Yeah, that's indeed. Yeah, we're skipping that. So now we're just going to write these values out. Let me break here so we can see the entire thing. So now we filled in these entire 8 bytes. Compare these with mine here: E3, 4D, 4E, C3, E5, 4D, 4E, and C3. That's correct. Yes, that's very good. So we got that correct. Yeah, that's the entire thing, right? That's the entire fall through when in the 30 hex thing. So we're in the 30 hex handler, and that's the fall through if it's not 0 or 1. Yeah. So I think the 30 case is completely implemented now, and I need to yeah, I do not encounter any 10 or 20 yet because there are outputs here, so that's not happening. Oh yeah, so we're only doing the first column. Well, that's the first column and that's the second column. Are we doing the second column though? How is that already filled in here? We're doing row 1, as in the second row. And that's the first column though. How is this data already filled in? Or is that the next byte? Wait, what? Because where did we end up now? So this is our temporary table. We started at this has the wrong name though. Decode level data for temp buffer. Yeah, where are we in the source here? 5889. 5889, that's our table, right? 5889. That's this guy. Well, I mean, we stopped at 5888, I assume. Yeah, so these are sets of 16 bytes. Yeah. Yeah, so that table is 16 bytes wide. Yeah, what did I call this? Like the ceiling adornments. This is that's an array of sets of 16 bytes. E1 F8 is our target pointer here. Yeah, so this instruction did 8 bytes at a time. I wonder if it's going to write out more now, because I'm still confused why I'm writing in the second row here, in the second column, I mean, because yeah, that doesn't make sense, because I literally only did the first, so I'm starting at Y1 and I'm only doing it once, and I'm starting at X0 and I'm doing it once. So that means we do interpret the next byte. Okay, I was looking for the pointer for that, right? So let's see. I want to go continue from this return. Okay, so we call this function, so we jumped into here, 5A43, that comes from up here. Okay, let's just continue so I can see where we came from. Okay, we're skipping 2 bytes, right? So that's where we are, 5D5E. Yeah, we're skipping, so we were handling 3280, and now we're doing E007. Oh yeah, that does make sense, because we're doing 4 rows at the same time. Each chunk has 4 rows horizontally. Yeah, that's why why we're staying in the same chunk, but still doing more data. Okay, so it does make sense. Okay, so now we're handling E0, which is the fall through case, which is just copy 1 byte, which we do correctly. Yeah, that's this iteration. So we are doing E0 now, I think. We're loading, wait, no, not this. Yeah, this one. So we're loading E0. Yep, that's this guy here. And we're checking whether the top nibble equals 0. So we're getting the top nibble. That is E0, of course. And then we're falling through, right? Because 10, 20, 30 doesn't match. We're falling through and copying 1 byte. Okay, and we're doing the next one, which is 07. Okay, that's going to be, so we're taking the top nibble, that's 0, and now we're in the first case. Okay, so now we end up here. And what did I write out? I wrote out E1 and E0, so that's going to be completely wrong then, because this is the only correct one. And yet I didn't write out this top nibble equals 0 though. So we have a 30. Yeah, so the 30 is this guy here, and then we have a top nibble fall through for the E0, but that's not correct. This one is not correct because we don't have an E1 here. We have an 07. Oh, yeah. I'm incrementing too much. So the E0 shouldn't increment over the 07 here. Yeah, so and that's because there's another E1 here. Yeah. No, the fall through doesn't handle the next byte, I think. Yeah, because now we had 07, right? So we are pointing to 5D60, which is this 07. Yeah, we have to handle that separately. That means that I shouldn't do in the fall through, I shouldn't increment this guy. Because we already do this, right, let me see. So it's this one here. Yeah, we're already doing this here. Yep, so level data index cannot be incremented here. I have to verify this in the code though, so I have to find the fall through again. So we're around 5A15. Yeah, so the fall through happens here. And where do we jump? Yeah, we jump back here, right? 5A08, yep. And the thing that contains that pointer is DE. That's 5D60, right? 5D, yeah. So it's DE at this point. So we're loading that value, writing it into the output temp buffer. Oh, and we're increasing both, incrementing both though. Do we not? Oh, are these guys separately incrementing? Yeah, I think all these cases do increment DE as well, so. Wait, so let's double check. So that case for the 30, okay, that calls 5A50. Okay, when it increments twice, okay. So at this point in time, before we enter our selection, whether it's 10, 20, 30, or fall through, that pointer hasn't been incremented yet. So what I'm doing here is actually slightly wrong by doing this increment here already, right? That is technically incorrect, but that means that the increment twice that happens in the 30 case, which is this one, it should only happen once. No, it's wait. This one here. Yeah, so we have doing it once here, and then I'm doing it here again, and I don't think I'm doing it another time. Well, in each of these cases, of course, but only once. Whereas the game does that twice at the end of the 30 case. But that means that I can't do that here. Yeah. Yeah, so now we have our 07 here. So now this is the case where we were looking for, right? Top nibble equals 0, because for 07, the top nibble is indeed 0. And we're not handling them, we're just copying the byte, because we're actually falling through, I guess. Well, no, we're not doing anything. Yeah, and we're just going to the next one. It's weird that it gets written out, though. Who writes this to the output buffer, though? Because this is being triggered. Oh yeah, okay, that would make sense, because yeah, it was still executing this block of code, and then it just did the fall through. So yeah, so now it's completely skipping the 07, and yeah, this isn't implemented yet, so it doesn't have any effect on the output buffer. And of course I'm indexing my output buffer separately, so it makes sense that the E1 gets copied right there, whereas it should be here, but that's fine. We have to implement this first for that to be correct. So yeah, is this jump 5A36 is the jump we're going to take. 5A36, that's here, and we are jumping or running until here. We have an unconditional jump. Okay. We're loading 0 into C, fine. We're loading the value of DE again, which would be, so let's follow here. We're following the jump here. So we're loading 0 into C, we're loading the value DE 5D60, that's 07, right? 5D60 is 07, so we're loading the byte. And we're taking the bottom nibble, which is 7. Okay, that doesn't change, of course. We're saving that into the B register. Of course, the B is going to be the counter for this for loop. Oh, so we're writing 7 times 0 into the output. Oh, that really, that can't be correct though. I mean, I think it's going to backtrack and overwrite these with something else, because why? Yeah, it's writing 7 zeros if I'm not correct. Yeah, so we're taking the bottom nibble, saving that into the loop counter. Then we're loading 0 because we wrote 0 to C, that's hard coded, to whatever HL is pointing to, which is E1F9, which is the next byte, right? That's this one, yeah. So we're loading 7 zeros here. Weird, but okay. So we're taking the top nibble off, that's meta, right? That's the counter. No, the bottom nibble. Oh no, it's the bottom nibble. Okay. So it's the bottom nibble, and then the entire value. Oh no, he's just writing 0. Okay. Yeah, that's all that does. And then the value we write is this, but 0 as an output. Comparison, that's fine. Oh, I already used that, right. Yeah, okay, so we have 7 zeros now, and we're putting E1 in the next one. Sure. Let's see if the game does the same thing. I'm going to break after the for loop. Yeah, so we're incrementing DE, that makes sense. We're going to the next byte, and we're jumping to the start again. So I'm gonna stop here, and we should see 7 zeros here. Okay. And then we're doing, so the next byte is going to be E1, which is the same thing, right? So we're going to write E1 here. We've already seen that, that's fine. That's the same routine as the E0 from before. We have, because we have that correct here as well, right? So it's only copying 1 byte, it's the fall through. So no, 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 and then we do the fall through. And that's it. So we've written E1 here. And then the next byte is again 07, so again 7 zeros, sure. So yeah, so we 07, the top nibble is 0, so we do the first one, and taking the top nibble. Oh no, I was looking at the wrong one. I think it's this jump. It's this jump. Okay. Yeah, so we're loading 0. We are doing that 7 times. So I'm gonna break again just before we jump away. Yeah, we have 7 zeros, so this one is correct as well. And then what is the next one? 38. So we are in the 30 hex thing here. The top nibble equals 30, and then we have 8 minus 2. We have 6 left, so we do like, where is bottom nibble used here? Yeah. So this is those minus 2, right? That's 8 minus 2 is 6. So we're indexing now the 6th set of 16 of the array that contains the sets of 16. That should be... Why are these all zeros? So top nibble 0. Okay, right. Why did it stop here though? Right in E1. It should have continued with... crap, I clicked somewhere. 5D63. Yeah, why does it not handle the 37 and stuff? So it should have 2 of these guys. And then we have a fall through, yes. And then we are writing indeed, that's the E1 case, yes. And why do we stop here? We should continue with the next 7 here. Oh. Oh, wait. We're only doing 4 bytes. And that was 4, I think. Yeah, we started at E0. No, at 3280. Yeah. So 1, 2, 3, 4. Yeah, that's not correct. We need to continue. I need to know what the exit condition is for that function, though. The exit condition for that specific loop, because yeah, that limit here doesn't make sense. I thought it was hard-coded, though. So yeah, we jump every time we jump back at the top of this function, there's a condition, right? 5A08. Is this the exit condition then? 5A12? No. 5A4C. So we do jump far away. 5A4C. Oh yeah, this is the exit condition. Okay. Yes, because then we just leave, right? So we're loading the base pointer again, E1F0, which is the base pointer to our temp array here, our temp data output buffer, the temp buffer, I guess. And then we're exiting the function. So this is indeed the exit routine. Yeah, there's an end marker here instead of doing four loops. Okay. So what are we checking here? We're loading L, that's the pointer E208. Oh, yeah, we're checking. Yes, whereas I did 4 because, right, so I assumed 4 here because we have 4 sections of 8 bytes. Our temp buffer contains 4 sections, right? Those are the 4 rows in the chunk within the room. And I assumed that it will be just, we're handling 4 or 1 at a time, but only 4 times. That's why I did a loop of 4 here. But there's a different exit condition. So basically, it's checking where we are in the thing here. And at this point, we are pointing to E208. So we just did the write of these 7 bytes. And now we ended up here, and we still have 8 bytes left that we have to fill. So that's what it's checking. So it is checking whether so E208, so HL contains E208, and we're loading the 08 part into the accumulator, and we're checking whether it's less than 16, x10, I think, right? So we're checking whether it's 16, and that would be the case if we are, if we are at the front at E210. But how does it not trigger? Oh no, it's literally checking for E210. Okay, that means I have to keep track of, I mean, we have that variable, we have level data, no, we have output or temp buffer index. Yeah, so I have to do a while loop while the temp buffer index is smaller than 32, right? From 0 to 31. I think that's the case. Let me try that really quick. That makes sense, right? Yeah, I think so. That might infinite loop, but let's see. Yes. Yeah. Because now we are doing more than we didn't stop here. So we are indeed doing the seven zeros here, and then we encounter a 30 again with an E0. Is that correct? Well, not really, because we should encounter the 37 here. Well, that's a bit weird. Oh, no, that's this one here. Yeah. So we have two zeros. That's 07 and 07 here. We have the fall through, which is the E1. Okay, and then the 07 again, and then we hit 37, which is this one. That's why it's 7, because there's 7 bits left after this E0. So we have to do, well, so we're in the 30 thing again here, right? And then we have 7 as the bottom nibble. Wait, yeah, we do, right? Yeah, because it's 37, so the bottom nibble is 7. So we're in this case, 7 minus 2 is 5. So we're indexing the 5th thing in that index, in that array. But why aren't we? And we are copying 8 bytes, though. That's not good, because we're overwriting our buffer here. Okay, let's see what the game does. So we're at 08. Yeah, we're here. So we are going to write E0, right? That's going to be... Oh, no. No, we wrote the E1. Yeah, and we're doing our 7 zeros. So we ended up here now. And now it's 37. This is completely wrong. This shouldn't be E0 at all, because we're handling 3780 here. So this is correct, but we're doing the wrong value. Because yes, we do have to do 8 bytes. And at this index 5, so 7 minus 2 is 5. So we have to index the 5th of the 16 set of 16-byte array thing, the adornments, right? But why are we copying E0 here? That code should just work. So we are doing this. Just in case we're in the other cases here, I doubt we will be, because like bottom nibble is 7 clearly, right? I mean, yeah, so I mean, yes, we're copying from index 5. 7 minus 2 is 5. Yeah, we're copying from index 0. So this works from index 0, that works, but this does the wrong thing, I think. Okay, let's see. So we don't exit the... Okay. Oh, no, we are jumping over. Yeah, we're not exiting yet. No, okay. I thought we were exiting already, but we're not, clearly. So we're loading DE, which is now the 37 here. Yes, 37, and then we're taking the top nibble as a 30. So we're going to the 30 thing here. That's this one here. This one, yes. So we're jumping to 5A43. We're calling 5A50. Let's go into this one. I mean, we've done this though. 5A50. So we're loading the 37 again. And then we're going to the next byte. We're taking the bottom nibble, which is 07. That's not 0. That's fine. Yeah, we're decrementing twice. That's also not the case. So we're falling through. So we have 5, we're indexing 5, which we're loading into B, right? B was used for this one here. Okay, so yeah, so we're loading the base pointer of the array at 5A79. We're indexing the 5th by timesing it by 2 4 times. Okay, that becomes 50 hex. That's fine. And then the pointer becomes 5AC9. So we are now here 5AC9. Yeah, that's definitely not E0 or whatever it is here. Like, this is completely wrong. We have 33, 84, 37, etc. Okay, so that address should be, we have that, right? The base index. Yeah. I'm going to, oh no, I'm going to add the thing again. So we have the mapping offset, so we have the exact same number as in the game. 5AC9, yeah, exactly the same address. Yeah. So yeah, that should point to 3384 and stuff. Okay, so we're doing this 8 times, loading the value. 5AC9. Oh, 5AC9. Did I completely miss that? 5AC9? Wow. Oh yeah, no, because our yeah, sure. I was looking in the incorrect thing. It is indeed C2 or C9, yeah. Okay, that's weird. So what did I write? E2? No, E0. I wrote E0, and that is indeed here the thing that's here, so it is correct. Okay, let's see. Let's continue. Rotate left. Okay, I mean, that's going to be correct though. Loading DE into A, that's E0, which we then increase or increment the EM right out. Yeah. And we're looping again. We're loading the next byte, which is 0. That's correct. That's this guy, 5ACB, yes. We are loading that into okay, then we're loading CC. Okay, so we're loading the next one. I might be doing something wrong here though. And we're writing that out. So so far we're still correct because we're writing a 0. And then we're loading the next one, 5ACD. Yeah, it might be correct though. These might always, because it's always going to skip one, right? So it's going to take this 0, this 0, this, no, this. Yeah, it might be correct. So let me break at the end of the loop. Yeah, it is correct. I mean, sure. I wonder if it will backtrack though, because I can't remember. Oh, of course that's correct. Of course. So if we actually take a step back and look at what we're painting now, so we're painting this area here, right? So we have the first 4 lines are done for the entire thing, for the entire room, because that's the top part, that's the ceiling. Now we're doing the adornments horizontally over the thing. And of course, only the adornments are in the first line, but the lines below that are empty. That's where the game area is, where we can move around. So of course it's E0 and E1. So the E0 and the E1 and the E0 are the left border of the 3 lines below the adornments. Yes, of course. So I'm just going to need a pointer to, or 5A08 is where we are. Yeah, so I don't lose that. 5A08, yeah, the start of the function here. This one can go too. This can go away. Yeah, 5A08 is what we need. Okay, I'm gonna disable it and we're gonna check again. Yeah, it's this area here. Of course, that's just one at the left and then it's empty for the rest of it, of course. I mean, we didn't really see this, because I'm assuming that should be part of it, right? Tile viewer. Yeah, so, oh yeah, maybe we don't. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. So the circle thing here, the portal thing, is the next chunk. So the chunk ends right here. So yes, that's obviously empty space. So that's correct. Let me look at the output now. I'm going to re-enable the first. Yeah, add some more chunks to the thing here, because that's not enough. So I'm gonna start again at the top. I'm going to do the entire two. No, let me do. Yeah, let me do the entire two rows, the two top rows. So we're going from y0 and 1, and we're doing x0, 1, and 3. Okay. Yeah, that should dump the entire top half of the game. Right, so we have our our ceiling here. That's correct, and then we have our adornments and the top thing, like the second row. Right, so let me pause here so we can see. So we should have everything above this line here should be in the game. So lots of empty space. Then we have the circle thing we should see, empty space, and then this border thingy. That should be all in there. Yeah, so that should be this data that's highlighted in the thing here. That's this. It's hard to visualize though, but sure. And that should be copied in E600, right? So we have our 5 E's and 5 F's here, and then we have our top data. So E3 4D, we did verify that. E5 4D, so that's these guys are the is this line here the complete adornments of the thing, of the ceiling. And then we have E0, E1, E0, E0, E1, E0, and we have wrong data, right? Because we have BF6C, that's not in the thing here. That's incorrect. Okay, so let's see if we have a different thing here. So the first ones are correct. Those are the ceiling things. Then we have the, yeah, this one is correct too. That's the one we just did. That's this guy, this, and this. And then the next one, so we have a 30 zeros, we have fall throughs. These should be correct though. So we have E5, that's this guy. And then zeros, yes. Again, zeros, and then C859EA, that's correct as well. And then this one seems more complex. So we have a fall through, a 30, fall through. We have a couple zeros and I mean, this should be correct as well, right? So we have, and it isn't because it should be E5 for E again, and we have 4-1, we have this nonsense here. So that means, I mean, I'm not seeing any 20s or 10s, right? Which is the two parts of the algorithm we haven't implemented yet. We only see stuff that we know, and we're still making a mistake here. Yeah, it's the third, it's this guy here, right? So this is the first one, the second one, and then the third one is where we go wrong. Wait, am I? Yeah. So that's the first one, second one, and the third one, and that should be E5 for E and stuff, and that's completely wrong. How can that be so wrong though? Okay, let me think which thing to enable here. So we are in row 1, column 2, and we're only going to do that one. Okay, yeah, that's the big one. Yeah, 4118, that should be E5 for E, etc. Yeah, immediately the first one is already incorrect, right? We're doing a writing of 41, whereas that should be definitely something else. That means I should, how can I figure out when to stop here? Because if I break on this one, then it's already too late because the temp buffer has already been written, right? We're only interested in writing in the temp buffer here. I can put a watch point here and then just count, I guess. Because we have to count, so 1, 2, 3, 4, 5, 6, 7, 7 times, right? Is it 7 time? What? 1 second. So the 7th time that this hits, actually that's the start of the function, right? I can actually stop at the start of the function, I think. So 5A08, yeah, I think it's just the 7th time we stop here. Yeah, let's see. Okay, 1, and then if I continue, we should fill this in with the first chunk. And of course, this data isn't gone, right? That sucks. Okay, let me reset and hope, let me reset. Actually, let me take away the power, so it's definitely gone. Yeah, so now we have a blank canvas here, so we can see what it writes out. Yeah, E600, that's where it's going to start. Okay, it's going to break for the first time, and it's going to fill in the temp buffer here and the first chunk of 4 lines. So that's 1, right? And then 2, 3, 4. So the top row is done. The top 4 rows are done. And then now for the second, for the first chunk in the second line is fine. We have that one correct. The second one as well. And now we're doing the incorrect one, right? Yeah, because over here it's going to start to diverge. Because if I, just to be certain, if I undo this, and compare, we see that we have E34D here, that's correct, and then the second chunk as well, that's also correct, but then what we write here is incorrect. This is a 4181, and if I re-enable what I did, then we only do this chunk, 4181. Yeah, okay, so that's definitely correct. Okay, so we're at the correct position now. And now we have to look at the pointers and see where we're pointing at in the data. No, I want the other one. No, I didn't want to do that. Wrong button, or wrong item, I guess. So we're pointing to 5D, 5D. Don't need you either, 5D, 5D. Okay, so we're starting with a 32, which is a 30 variant. 2 makes it 1, I think that's index 0 of the fall through, I think, right? Are we correct here? So we're in the 30 variant, and then it's 32, right? So we are taking the bottom nibble is 2, so we're falling through. We should be indexing into the index 0, actually, as in 2 minus 2. Do we do that? No. We're doing a fall through immediately, so we're not doing the 30 thing here. So we're writing 41. Where does the 41? There's no 41 in the vicinity here at all. How can that be so wrong? Wait, I'm correct here, right? Yeah, we're loading 5D. Have we no, yeah. So we're correct here too. We're doing 1, 2, 3. So we're pointing at E690 or no? Oh no, we can't yet. We have to, of course we're pointing here in E1F0, right? Yeah, we're not writing it in the output data yet. Crap. And so we're pointing at 5D, and what is the other one? 5B C8. 5B C8. Oh, so that points to 635D. So that's the pointer. Yeah, so if you look at the hierarchy again, 5B65. That's this one here. Yeah, okay, so we were here, right? Yeah, 5B C8. So this array is this guy, the array pointers to tile data. Okay, so we are looking at 635D, as in the one we're currently looking at, 635D. Would it be that one? Do we still have to load this here? Maybe. So first we're checking the exit condition. That's fine. That's not going to happen. So we're jumping over, yes, and we're loading DE. So DE is, well, no, we're looking at 5D. So we're loading 32 hex. Okay, let me write that out. That's level data index plus ROM offset. Oh, no, that's okay, crap. Yeah, it's, I need to add the thing, like it's this one. No, DE starts at, no, it does. Wait, no, it's this one, right? 5C40. I think it's that one. Did I have a variable for that? No, but that doesn't matter. 9C40. Oh, wait, no. Okay. So we have to do the addition here. So 95D is the thing I'm looking at. 95D, it's going to be this one. 95D. No, that's both before these guys. Okay, we're coming from 59F6. Let's go quickly see what we are, where we were called from. No, that's not that one. B1, B4. That's definitely not correct. 9dB8. Maybe we jumped here though. Yeah, that's also not the case. Crap. So I can't trust the stack pointer here, or there isn't any, I guess. Or pointing to the previous function, I mean. Wait, level data index. No, I'm doing the wrong one. Oh crap. Level data has been assigned. Yeah, I've already assigned that pointer, right? When we were loading the thing. Yeah, of course. It's this guy that's confusing me. So we're indexing in compressed style data array. Yeah, it's this one. It's 5b65 minus the, okay, that has it subtracted, so I have to add it back. So it's this one, 5b65. Does that make sense? No. Well, what is that 9b65 though? I mean, that's below these guys, so that doesn't really make sense to me. Okay, let me just get the map level data index, and I mean, that's going to be 0, right? It starts with 0, I think. Yeah, 0, 1, 2, 4, 5, 6, 7, 8. What do you have? You're a pointer, I guess? No, you're a 16-bit value. Oh, no, 4 is correct. FB20. FB20? That's quite high. $177, which comes from what? Oh yeah, that's the index into the room data. Okay, sure. Okay, where does the room data come from? That's going to be a in-memory location without the mapping offset. That's fine, so I can compare more easily. So we're loading at 9dB2. Okay, yeah. So yeah, that's the room data array. So 9db2 is, yeah, that's what would be correct, right? So we're doing 4 ones, right? And then we're doing 31. Yeah, so we are here, and then, and that is per column, so 4 chunks per row. These are 4 columns, and it's again the 1 though. Do we have to index that further? No, right? Oh no, wait. I have to index that. Yeah, I do have to index that because. So yeah, of course, I was confused by the ones because the ones are the top row, right? So this is an array, the base of the array, and we have to index that further. This is the entire stage, like the entire scene, the entire room, right. Yeah, so that's the room data is indeed loaded from that address, and then we index into that address by yeah, that's what we're doing here. And then that would be the start. So the start would be the tile data index. So 177 is indeed the index in that thing. Yes. Okay, right. So we go 177 in this array. So that would be 9db2 plus, I mean, what is 177 is B1. So B1 plus 9db2 is 9E63. Okay. We start with a 0. Okay, fine. Yeah, this is incorrect then, because so 9db2 is a, okay. So let's print out what we actually load here. When we're indexing the room data, the tile data index equals 177, and then let's see what we read here. So get compressed tile data pointer at index 177. Okay, so it's a reading of that pointer that's incorrect, I think. No, I want the definition here. Oh, is that a pointer? Oh, is it B100? Oh, wait, that's a pointer then. So B100 is the pointer. Okay, that might be the case. Okay, sure. So that would be this value here, and that's incorrect because that's FB20 and that should be B100 if I'm not mistaken. Because we're requesting this index. Oh, we're doing multiple bytes. Okay, wait, no. It's more complex than that. So we're doing the index times 2 because it's a 16-bit pointer, right? Oh yeah, and then we're writing out the values. Okay, no, I shouldn't do 177. So yeah, that was incorrect. So we're starting at 9db2, right? And then we are adding B1, that should be B1 times 2, which is 9F14. So 8F05. Also different 8F05. Is that something? Maybe. Again, in memory value. So I'm not subtracting the 4000. 3B20. So room data is a pointer and this is an index. So 5D, okay, so 5D80 and then index 0 would make it. Wait, I might be, yeah, wait, I have to make sure that don't miss the thing, the ROM offset here. Okay, where was I? Yeah, get room data. So this guy, room data array, yeah, that's going to be, because that's referencing the ROM data, so that's going to be ROM based, not memory based, right? So I have to add the thing again, the mapping offset. Okay, and let's add this one here too. So at least we're working in memory world now. Okay, so 9080. Yeah, okay, that's a room data array, and then index 0 is indeed 9db2. Wait, that's ddb2. That should be 9db2. And that's literally the first pointer in the thing, and it says ddb2. How is that so wrong? I mean, that can't be wrong because we literally decoded like five chunks already. So scene index times 2, 0 times 2 is 0, of course. So we're indexing literally at that value. I mean, that should just be 4000 different, right? But it's hard to, yeah, so 9db2 becomes ddb2. Wait, oh yeah, no. Of course, this can't be added because the values in memory are all already referencing memory, of course. Yeah, that's the pointers that are included in the ROM are ROM based, or memory based. That's why. Okay, sure. That makes sense. Yeah, they're pointing straight to the memory. So 9db2. Okay, so that's the index 1. So 9db2 is here. Okay, so we start with, okay, that's our base pointer. Then we index 177 in that. Is that correct? We have, right, let me see how did that calculation work. Loading the room data, that's what we're doing. So we're having a tile data pointer of 3b20. So we have our room data, and then decode tile data. Tile data index is 177. Okay, so let's verify that. And that is based off the compressed tile data array. I mean, that's too far though. We have to use the, okay, yeah, the room data is being indexed here, which is 177. Okay, so right, we do know that. Oh, well, no, what I wanted to know is y and x, I guess, for room y, x and y is at y times 4 plus x. So that's just an index that we have to calculate, because 177 is indeed the no, actually we're reading from room data, so I need to know that number too, right? So I times 4 plus x. What's wrong? Oh yeah, I'm missing something. Tile data index, that's room. No, that should be x and y, and then the index, right? And that then gets indexed into the tile data. Okay. So room that we are at x2 and I1, well, y1, and that is 6. 1, 2, 3, 4, 5, 6. Is that correct? No, 0, 1, 2, 3, 4, 5, 6. Yeah, okay. So the 6 is correct. So that's being indexed into room data, and that appears to be 177. So room data is at 9 dB2, right? So 9 dB2, right? Okay. 0, 1, 2, 3, 4, 5, 6. So we're at B1. Okay. Oh no, these are pointers. Oh, no, these are not pointers. So what do we do with this? Oh, B1 is 177, I guess. Yes. Okay. All right, it's like this. So room data index 6. Is it 6 or 5? We start here. 0, 1, 2, 3, 4, 5, 6 is B1 is 177. Okay, yeah. So that's correct. And then so this number gets put into the tile array, I guess. Yeah. Okay, so 177 into this one. Okay, that's B5, 5B65. Okay, That's this guy, and that's a list of pointers, right? So that's a tile data, no, that's tile data array. And then we need 177, so 5b65 plus b1 is 5c16. That's quite down, because we're already with the level data C1 here though. 5c16. Oh, wait. No, and we're multiplying even, so these are pointers then. Yeah, these are pointers. But B1, that's so far. That's incorrect, I think. Because that's like it's the 177th pointer in this array, but we're overlapping with the level data for scene 111 here. So there must be something else going on here, because that's not correct, I think. Because if you looked at the other pointers, they were small, or the indexes, they were smaller, right? If you looked at, so room data is at 9080, right? 9080. Yeah, these are the room pointers. And so we started at, the first one is at 9db2. 9db2, that's this guy, yeah, that's the first. So we have a limited set of room pointers. Okay. And then the sixth thing here is B1. And all the other ones were very low, or relatively low. 111, 31 hex, 68. Okay, sure, a bit larger, but then we have B1. And we go even higher with E4 and D0. So, and we index that in 5b65. But that's not big enough, I think. Because what is this? Are these pointers or not? Compressed tile array. Yeah, because that's a 16-bit pointer, right? So the first one here is 5c3d, then 5c40. So 117 in this is way beyond what we have, though. So I think I'm making a mistake there as well. I don't think it's the decoding algorithm of the tile data itself that's wrong. I think it's this indexing that's wrong. So how are we going to find that? Because that's a couple of functions up. Okay, let me put a watch point on that B1 then. That should give us an idea where it is used, because it's only used in one spot, of course. Well, I assume. So let's go back to 9db2. And then we have our B1 here. So I'm going to look at my watch points again. And breakpoints. So let's disable this one and that one too. Okay, so this one can go. I'm going to add the one to the B1 here. And I'm going to have a read memory watch point. I'm going to continue and reset. Yeah, we have already triggered it, but that's fine. Whilst we're resetting. Okay, let's see. Yeah, we do break, and we break just before we call decode level data pointer chunk. Okay, that's good, right? Did I give that function a name? Doesn't look like, because there's data in between here. So we're loading the room data array. Oh yeah, that was the E601 thing, EO61. I think I remember that. Well, maybe not. So 9db8, that's the pointer to the B1, okay. Okay, let's go in this one then, because that's being given, that's up until here it's still correct, right? We give it B1, this function. Let's see what this does. Decode level data pointer chunk. Okay, so now we have to, to get the chunk, we have to read the offset into the tile data array. So let's see if that is correct. And so we're taking the bottom 7 bits. Oh, wait, it's not one. Okay, that doesn't make it 177 then. Okay, sure. B1. Right. That makes more sense. So B1, we take away if we take away the top bit, that is 49. Okay, that's what we're doing. Right. That was I forgot about that. So I'm sure we can see that in the code as well, right? At least I hope so, unless I forgot doing that, because I don't see it being done here. Yeah, so we're taking 177, but we have to take off the top bit. I think I forgot to do that. So wait, yeah. So we're adding it with 7F. That becomes 3-1. Is that correct? Yeah, 3-1 here. Yeah. And suddenly the index becomes 49 instead of 100 and etc. Decode level data pointer. Yeah, I think. So let's see what the actual address is when we add this pointer together, right? That would be after this one. So now DE contains the correct pointer 5D. Okay, so we have to end up with 5D and not 3B20 here. So if I do this, that has to be, yeah, it has to be an 8-bit value, right? I think, yeah. Equals index and OX7F. So we're taking the bottom 7 bits, right? And then we use that instead of the index. That's probably going to complain about, no, I mean, first, okay. I'm not complaining either then. Yeah, so 177, and that becomes 5D. That was a bug, yes. That's now better. So 1D, 5D, okay. And now we have top level of hex 30, and we see that our temporary thing is already a lot better, because that's what we were looking for, right? Instead of, yeah, we overflow that array a bit. So that's what else do we see? We have 30, we have fall through, we have 0. Yeah, so nothing we haven't seen yet, so this should be correct. That means I'm going to remove a couple of these now. So our algorithms are fine, but these guys can go away for now. So it's a bit cleaner. Okay, so we have a 30, we have a fall through, a 0, a fall through, a 0, and a 30. Right, now I have to stop again at yeah, I can just do the 6E or E600 buffer. That should be fine. Let me start. So this is the first row. Actually, I still have the pointer to the function, right? Where we could, yeah, it was the start of the function. Right. So this one can go. It was 5A08. Yeah, well, is this starting function here that I need to break on? Actually, I'm going to reset because I don't know where you are. I mean, actually, it was going to do the correct one, of course, because I was at the correct spot, but that's fine. That's fine. So let's reset. It was the 7th one, right? 0, 1, 2, 3, 4, 5, 6. So 6, yeah. So the 7th iteration, you can break. Now we see what happens here. Okay, the first one. Okay, yeah, I didn't reset, but I mean, I should reset. Yeah, let me reset, because otherwise it's hard to see what gets overwritten, because the entire thing is here now already. Now we have a blank canvas here. Okay. All right, first one. That's good. 2, 3, 4. Then the first chunk, the second chunk of the second thing, and now it's the one we are interested in. So it's going to add it here, and it should be this thing, right? E3-4D. So let's see. Wait, no, this is the... I'm doing the incorrect one, I think. Wait, let me see. I'm doing the second row, the second thing. Oh, no, I need the third one, right? So x equals 0, 1, 2, 3. No, that's the... Okay, let's do them all for a second here. Well, at least the top two, E3, E5. Oh, no, yeah. This is the first one, this is the second one, and this is the third one, of course, yes. But... So we have E3 for D for E, we have E5 for D for E, C3 and stuff. We have E3, oh, that's incorrect though. Yeah, we're off by something here. And then we have E3, and this one is off too. So these are still wrong though. And then we have, and exactly like the other one too here. So this E0 shouldn't be there, and we should have BE here. Yeah, so there's still a bug in there though. The C859EA is correct. And that is the third row though. That's also weird that is correct. Wait, so this, and this is 1. This, and... Oh yeah, that's 2. Okay, yeah, that's 2. And then 3 is incorrect. That should... I mean, it's almost correct though. It's the inverse, right? Even instead of E5 for E, we go E3 for D. Like it's almost, it's like literally the same thing that's here. That's the top row that's repeated. That is a bit strange. I mean, I guess we'll have to figure it out too. That's we can't help that. So although our temp buffer here, like we're at this point now, right? We did just write out the third one. And if I look at my temp buffer, that is actually the same thing though. So there might, okay, so the decoding might be correct. It's just a copying that might be, there might be a mask put on top of that. Right, because it is indeed correct here. I mean, at this point in time, the temp buffer, so we wrote the third column of the second row. That means that the temp buffer hasn't been touched yet. Yes, so I think that copying over stuff, which is this one here, write temp buffer to output, that might do something strange. So what I'm doing, I'm just taking these 16 or 32 bytes here, I'm dividing it by 8 in chunks of 8, so 4 times 8, and I'm copying this to the first line here, and then the second one 32 bits beyond that, and then 32 bits beyond that, etc., etc. I'm not manipulating the values, and apparently that is what needs to be done. Let's see. Now we have to find where that code was that writes out the temporary buffer, though. So that happens at the end of this function, I assume. So at this point, we have the thing written, right? That does the temp buffer. So we have a temp buffer written. Yeah. So we decoded that, which is the exact same thing, because if you look at my fourth here, that's also the same thing. So we're doing the fourth now. I just processed the fourth, and that is this guy here. And we have E1. Yeah. So yeah, the last one we do is this one, right? E3, 4, D4, E, etc. E0, E1, E0. So that's indeed the last one. Yeah, which is the last chunk in the row. So that is correct. Now we go see where we end up when we write that, because that has to be the next function, right? Is it this 5b3a call, perhaps? That's messing? No, that's not messing with us. 0408, that's the loop counters. Yes, so a3bb is the function that writes the temp buffer to the output buffer. So let me write that down. A3bb. No, I need a symbol file. That's quite high though. A3bb. Okay, so let's go here. So we set A to 0 with the XOR. Oh, and we're immediately jumping to A3CC. Okay, sure. And we're calling 45DA. So we're doing our block copy here, right? And we're returning here. What was 45DA? Let me look up that here. Push DE. Oh, we're indexing into DE. Okay, so the 0 that we got from before with the XOR is being indexed into the array at HL at 1806 into DE. Oh, no, HL is overwritten here, 45FF. Okay, what is 45FF? Indexed with 0, which is CD87. Oh yeah, we have a name for this. Oh no, that is the function. Oh, that's 45FF. I was looking at the wrong thing. It's over here, yeah. So that is a tiny array. That's literally just above or after this then. Wait. Okay, so 45FF. Right, we're somewhere right here in the code. That's why I was confused. That's a little array that's only 8 bytes long, right? So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Yes, of course. So we have an array of 8 bytes. Oh, no, or 4 pointers, I guess. Yeah, E5 C0, E8 40, EA C0, and ED 40. I wonder what that number is. So we're going to do so 45FF. Let me write that down first. And then the first pointer is E5C0. Oops. Yeah, that's correct. Oh, okay. So E600 is another pointer where we actually write the tile data. So before that, we have some other like maybe it does start here, but I think there was like a pointer to E600 hard-coded in the code somewhere else as well, though. So I mean, if they now add like a couple times 16 to that to arrive at E600, I'm sure, but otherwise I don't know. So these are the stages. I think we have 4 pointers and we have we have 5 stages. Yeah, not sure exactly why there are 4 then. So 45DA, that should give us 45FF, and we did 0 as an index. That should have given us E5C0, and we don't, because we have E1F0, and that's our temp buffer. Okay, that's weird. Get HLA into DE. So 45FF, I mean, how is that possible? 45FF is E5C0. Oh, we're popping HL. Okay, well, no, sure, that's fine. But we end up with EN. That's get pointed to the temp area, right? But now that we're here, I mean, I do want to get that. I should have gone in that function though. I want to go in there, so I'm going to break here and restart. Wait, so we do that multiple times? No, we don't. Okay, no, that's fine. So now we're loading the entire level. That's fine. We have to do that like 4 times 5, 20 times. Okay. I forgot where I was, but sure. I'll have to look in the code here again where I want to stop. Yeah, it's this one here. So 45DA is where we jump to. We do that multiple or only 2 times. Okay, so we came from. Oh no, we might have jumped there, did we? Oh yeah, it was the first thing we did in the function, right? Yeah, and then the block copy, we came from here, A3CC. Okay, so I need to go to A3CC. Okay, so it was this one that we need to break on. Okay, you reset. Okay, yeah, we XORed A, yeah, it was this function. Okay, so we set A to 0. Okay, so we're doing index 0 and we're calling this function. I'm going to go in here. So we're loading 45FF into HL. So we're indexing in this array, right? that's this one here, C0E5, and index 0 should be E5 C0. So maybe I am doing something wrong here. So get HLA into DE. Let's see. So we're doubling A because we have a 16-bit pointer, but it's 0, so it stays 0. Add A to HL. That should remain 45FF. I'm assuming that's correct. Yes. We're loading. Yeah, we're loading. Oh wait, did it not? Oh, it didn't dereference yet. So we're still at 45FF, which we're then. Oh no, we're loading the value. Of 45FF. Yeah, that's C0 E5 C0. It should be made into this pointer now. 46. How is that possible? So 46. Oh, no, okay, that's that's and then the E5. Yeah, it's writing it in DE. I was looking at the wrong thing. Yeah, so C E5. Oh, it's E5 C0. Did I not do that correctly? Was it did I say C0 E5? I might have swapped them around. So it's E5 C0, right? Yeah, of course. So we have the top part now for the chunk of data above the tile data for stage 1.1 or scene 1.1. So yeah, we do have E5 C0. We're popping HL, that's fine. And we're jumping to 45 E9. Oh, we're doing other stuff here. Oh, no. Yeah. We were here, right? This is the start of the function. I think we were. Oh, wait. Because here we're doing the same thing and we're falling through here. And here we're doing lots of stuff. I mean, that's just okay. That's just to figure out. Okay, sure. I think we're just crossing from this pointer to the E600 pointer, or no, it's going to be the temporary buffer, right? The E1F0 that's being calculated here. So I don't know why that's so complex to calculate, but sure. So did we jump to? Was it 45DC or 45D7? That's next room to load though. I think we jumped to 45DC, not sure anymore. So yeah, if we do all these rotations, then I'm sure we end up with E1F0. Yeah, which we actually do. Oh, well, we're popping it though, but sure. But that's irrelevant then. Okay, see, we were here. Okay, but that only determined pointer E1F0, so we're not doing that in our code here because that's just determining the pointer of the output buffer. We have our own output buffer or temp buffer, so that's fine. Okay, we're loading DE. The value, oh yeah, we're saving that pointer for later, that's fine. And then we're loading 0. Yeah, because we have to do it 8 times. We have to mask out the 4 here. We're swapping the pointers around. That's also fine. So yeah, I mean it's just a block copy, right? It's a block copy of the first chunk here. Yeah. Oh crap! I pressed play. Okay, but then we do the next one. That's fine. That's the 4th one. Then yeah. We have the first chunk, 2nd chunk, 3rd chunk. So now we're at the position where we are going wrong here. We have E34D in the buffer, in our temp buffer, so that's correct. We did the decoding correct, but for some reason that's going to be different when it gets copied here into, is it, yeah, this guy here. No, yeah, because because E5 for E is not the same as E3 for D, so something different is going to happen now. So the target would be E1 D0. No. Oh. Okay. That's why we have two sets of the temporary buffers here. All right. Yeah, we have two sets. That's why it's different. That means that the calculation of the temporary buffer address is indeed, so all those rotations we just saw, right? Those are relevant as well, because we have two buffers. Oh crap. Like this is super complex for what it is, right? I mean, they're just loading a set of tile data. And if we look at the data here, so the copying is going to be the same, I'm assuming, right? It's just a different base pointer that's being copied. Also, I'm going to give the other one a name too. E1D0 is the other one. Yeah, you go away for now. That's going to come back though. But so E1D0 and E1F0. This one has, this is a 1 and 2. So there are two sets apparently. So yeah, this one here as well. Crap, that does make it a bit more difficult. But I mean, it's fine. I'm wondering whether, like, first of all, what determines which buffer gets used, but did the first 4, 5, 6 chunks populate these this area too or not? That's my question. A3CC. Well, no, apparently not for that one. Oh no, I have to make sure. So no, I'm breaking at. Wait, does it do it twice? Okay, that's of course the same data. Now it's different. So I clicked 4 times, right? And now this is the 5th, so it changes. It changes again, and now it does something. Yeah, something more. Yeah, something triggers the writing out of the second buffer, and I'm not sure what it is or what data defines this. I mean, there's quite a few breaks here. Like, what is special about this third chunk here? 0, 1, 2, or like, yeah, the third chunk here. that we need a second buffer, or like keep the first buffer around, or have both at the same time. That's a bit weird. So A3CC, is that a start of a function here? No, this is a start of the function. I mean, the fact that the pointer changes is not enough, right? It's not just requesting a different pointer to write to. The algorithm is also different. So we must have skipped something. I mean, we're not skipping anything here, right? Like these do not contain the 10 or 20 variants that we haven't handled yet. But it must know that it's right into the other buffer, unless the other buffer is being based on this one. Like is a manipulation that happens on this one? Because wait, does it? No, it doesn't already exist when this is being called, right? Well, actually, that's interesting to know, because at this point the decoding has already happened, I think. Right. So let's see if we write our normal buffer out for the 6th or the 7th chunk here, whether this is already populated at this point in time. That would be interesting to know, because the algorithm that generates the top buffer might be different from our decoding routine that we already have. So wait. So let me stop at the start of the function here. Right, so at this point, well, I mean, we can't tell for the first one because the first 4 chunks do not use the second buffer here. But so okay, I'm already seeing something change here. So I think what I'm assuming here is correct, in that it is this function that manipulates the temporary buffer here into the other one, and it's not the decoding routine. So let's go to the correct thing here. So 2, 3, 4. Okay, so now we're in the first one, then the second one, then the, oh, okay, no. So yeah, it's already written. Damn. I mean, fine. Then we go, instead of looking at where the thing gets copied out, because the copying is the exact same thing, right? It's just the incorrect pointer. So if I do change E1D0 to E1F0 now, I mean, I can't change this. I don't know why it's the tooltip that steals the focus here. If I change it to E1F0, it's going to take the other buffer, the standard buffer, and I mean, it's going to mess up the game, I'm assuming. Right, so it's this thing here. Oh, it's mirroring. It's mirroring, I think. So the top one is overwritten by the stalactite here. That's fine. But these guys are supposed to be here, and I think it's just flipping and mirroring the thing. Yeah. That's going to be the case. Yes. So this is the mirrored version. Okay, so now we just have to know or figure out where this mirroring is happening. I mean, it has to be in the decoding algorithm, right? Like it has to be. Let's see, where can we break? So I'm gonna clear these, and let's see again in the code. So it's this one, I guess, 59E7. No, that just writes the thing, decode level data. Yeah. So, I mean, I guess it's this one. So now we're going to, instead of just looking at the bottom one here, we'll look at the top one as well. See where we trigger that. Okay, for the first one is irrelevant. I'm gonna continue. Yeah, that does the entire thing. Then the second, third, fourth, and now we do the next row. Yes, that was the first one. Now the second one, and well, wait, do I click already? No, I'm ready to do the third one now, right? So I'm going to go over it. Yeah, it's going to do the first chunk. It's not yet done. So yes, we're taking the top nibble, checking that's all irrelevant. So we're doing a 30 thing. Actually, I should just stop. Where are we? Here, because we jump back here, right? To this line. Yeah. Because I'm doing the first of the lines. Oh no, this is individually. Yeah, no. Okay, that is indeed byte per byte that we're doing. Okay, now we're doing that one. Those are the zeros, and now the E0, and I think we do 7 zeros as well. Oh no. Okay, so now we've done it. Okay. Although no, I should have gone out of the function or continued the function. As soon as this one gets written, I need to continue manually, step by step. Because I think we returned and then we came back to this function, although the thing was there already though. Okay, so let's do that again. Let's stop. Okay, the first one is ready. The second one is ready. Third is ready. Fourth is ready. Fifth. Oh no, I have to do times 4. Okay, sure. So then this one. Oh crap. Did I miss what? I mean, I missed it again, of course. Do I only have to count 7 times then? Oh yeah, we're at the top. Okay, sure. Yeah, so this is the first one. Yeah, then we have the second one, third one, and fourth one. Now we have the second row, the first one, the second one, and now the third one is ready, right? So I'm gonna break here now. So do the first row within the chunk, then the second row, the third row. Oh no, that's the third byte. Yeah. Now we're doing byte per byte. So we did this one first. Then we have 7 bytes. Then this one, 7 zeros, which is what's happening now. And then we do this byte, and then again 7 7 zeros. Then we end up here. So that's the 7 zeros. Then we end up here. Oh, that's immediately all the bytes. Okay, so now we are here, and I'm going to see, do we exit here? Yeah, we exit because we don't jump away. So, oh wait. So we are in, so we're checking H for E2, right? And that's the case because we're at E208. We're checking the address we are at currently. And we're loading H into A. Yeah, that's for the check. And we're jumping to 5A4C. That's the end of the function, I think. Yes. Okay. So we're doing that and we're returning from this function. But now we... Oh, it's this conditional. Yes. It's this conditional. I think this call is going to happen now, whereas previously it didn't. And this is going to be the mirroring thing. Yes. 5B and 5B3A, and I think I wrote that down. Where is that? Yeah, so it's definitely on this condition, but yes, here, this one, skip call to B3A is what we did skip. Now the condition was weird, right? It's calling based on the M flag. So I have to look again because I don't know what that is off the top of my head. So call M means, oh, if the sign flag is set, the current value is, well, we jump. So if the sign flag is set, I mean, I'm assuming that's this one here, and it is indeed, and it is indeed set. What could have set the sign flag here? I mean, it had to be the oh, we're popping AF. Well, does the pop instruction influence the flags? The memory location pointed by SP is stored into F and SP is incremented. Wait, what? Pop. Memory location by SP is stored into A and SP is incremented again. So yeah, we're incrementing this stack pointer. Okay, and what are we, okay, and then sure. So we're popping it off the stack, yeah. But it says, oh yeah, the flags are unaffected, all of them are unaffected. So definitely not because of this one. So that algorithm did indeed set something here. Wait, oh yeah, it's right here. It's just beneath here. So in our exit routine, we're comparing with E2. So we're with E2 and with 10. So, I mean, we're literally comparing this pointer here, right? Oh yeah, this is the second case. I mean, what I'm thinking is that if it ends up here, it does a mirroring. So first it checks whether the pointer within here, right? So we're either here, here, or here, right? So it checks, first of all, it checks whether the top nibble or the top, no, not the top nibble, the top byte in the 16-bit pointer is 10 hex. And that is only the case, wait, let me see. Oh yeah, that's this one. If we ended up at E2 10, so the bottom byte in the 16-bit pointer, right? So it checks this one. If this is 10, then we jump to the end, right? 5A12. Oh wait, 5A. So we're doing something different here. What is 5A12? Oh yeah, no. Wow, it's simply checking for E2 because it starts at E1 F0. So if it ends at E2, then it returns. So that basically means that once it's in the bottom 32 or 16 bytes here, then it can return. Okay. So there's two conditions to exit, right? If the lower 8 bits are 10, we don't exit. If they are none, if the comparison is not 0, so if it's not 10, okay, if it's not 10, then we don't exit, right? Because then we take the jump. So this is E2 10, right? If we end up here, then we do exit. In every other case, we don't. So this is the end condition, okay? So if it's not 10, or if it is 10, wait, if it is 10, why would we check for E2 then? That's so weird. So that makes sense. If it's not 10, if we didn't reach this position where there's 10 in the bottom 8 bits, then we continue on. But if it is, how can it be 10 though? Like, yeah, how can it end up unless we were indeed here? Yeah. So it did. Oh no, it did 8 bytes for this when it wrote this byte. Right. So we did end up here. I mean, it's always the same. I don't know what is comparison with E2 is. That's always going to be the case though, unless that's for this one, right? Maybe. So what could have set the sign flag though? And just before we return, we just load. Like, what could have set the sign flag? That's so weird. I mean, I'm gonna have to go through it again, I'm assuming, to see if that gets set. Perhaps the exit condition. Yeah, I mean, yeah. Okay, let's do that. Let me go back here. One, two, three, 4, 5, 6. Okay, and now it's the 7th. Okay, so the sign flag is set at this point. I'm going to do the first byte, then the E0, then a couple zeros, then the byte at E2, this one here. Meanwhile, the sign flag is set all the time here, I'm seeing, but surely that has to be manipulated by all this code, right? Then I'm going to do 7 bytes, and then I'm going to do the last one. Yeah, no, that does set all the bytes. So what are we pointing to? The E210. Okay, so we are pointing beyond here. That's fine. So now we're in the exit condition, right? So we're comparing the low. Okay, yeah. So this is the case. The sign flag is unset now. Okay, the sign flag is unset, so it wouldn't mirror. We are comparing with 10x, which is true, so we don't jump. So we're exiting. The sign flag is still 0. We're loading the top byte, which is E2, which also being compared, which is true, it's 0. Sign flag is not set, so we're jumping to the end of the function. Sign flag still not set, Wait, yeah, it's not set. We're loading the thing, the base pointer, that's fine. We are returning. Okay, so now we're gonna pop the accumulate, the AF, right? Oh wait, F is the flags, right? We popped the flags, of course. Right. Yeah, it's this one here. So the F contains the flags, I'm assuming, right? Yeah. These are, and the flags, of course, contain the sign flag here. Yeah. So now that's going to become 1 here. Yeah. So we're popping not only the accumulator, but also the CPU flags, which we saved right here. So this the sign bit is being, or the sign flag is being set before this. So maybe we're testing, maybe this test sets it. Yeah, so maybe it is indeed here. So what are we seeing? That's this one. No, we don't need this one, nor this one. Yeah. So it's the 59E9 that we need to check. Okay, so we're also gonna do that 7 times, I guess, right? So A is 1 here. And that's the 1111 that we saw in the table, right? That's what we get in here. So does this affect the sign flag? So the sign flag is currently 1, and we shouldn't do the double buffering thing. So is this going to put the... Is this going to put it on 0 here? That's the question. Yes, it does. Okay, so that's the 1 that came in. Then we have another 1. Yes. Again, sets to 0. I mean, it is still 0 now. Then we have another 1. That's the 4th one. Now we have 31. I need a table, though. Where is that table? So it's 5B65, I think. I didn't print it out in this case now. 5B65. These are pointers. Crap, I need to print that out again, I guess. It's the room data, is it? Also, I want only the correct room, which is on the first column, the second row, I mean, and it's the 3rd one in the thing. Yeah, I think this is the one. So at 9080, okay, that's 90B2. Okay, let's start here. Yes, so we have 4 1s and then 31. That's what we're seeing here. Yeah. So this is it's the B1. Oh, right. Of course. So remember how we had 177, which is the B1, right? What I forgot was to put the top, to take away the top bits, which is set in 177, and the B1 became 31, right? Index 49. So obviously the top bit is going to say, hey, you have to mirror this thing and use the mirror version. That's going to be it, like, pretty sure. Yes, of course, that absolutely makes sense. Yeah, because we're ending with 7F here. So is it the AND operation that sets the sign flag? Actually, no, it's just AND A. Okay. As defined. Okay, so it says as defined. What does that give me? Nothing for information here. But yeah, I mean, it's definitely going to be that top bit, right? I mean, we'll see, right? So 31 is not, that's not the thing. It's the B1 that's interesting. So 68 and then B1. The sign flag is not set. Let's see. It is set by the AND and it is immediately pushed. So the AND operation, how is that possible? Sign flag after AND I need. That's the truth table for AND. I do know that. It doesn't say anything about the sign flag. I mean, this is x86, which is, of course, completely... If the result is negative, as to its complement, which might be the case then, right? Yeah. Okay, yeah, I think that's the case, but sure. So we have to do this function if the top bit is set. It's as simple as that. So 5b3a is our mirroring function. Only once in the thing. Okay, what are we doing? We're loading 7. Where do we end? We have a loop here, and we return here. So if we don't jump out, do we jump out? We have a jump to 5b53, which is within the thing. Again, 5b3. Okay, so this looks to be everything here. Okay, and we have hard-coded pointer E1D0, which is our other one here, right? That's E1D0 is the other buffer. Okay, what do we do? So we're loading 7 into A, hard-coded, and we're adding A to DE. You have to know what DE is at this point in time, though, so we have to stop here and run through there. So now our bottom array is filled in, temporary buffer is filled in. Let's go into this function. And so we're loading 7 into the accumulator, that's fine. And we're adding 7 to DE. DE points to E1F0. Okay. So that will become this byte, though. So yeah, that becomes E1F7. Yes. And then we're loading E1D0. That's the base. That's the other buffer. Okay. Wait, did I name them incorrectly? I think I named them incorrectly here. D0 is 1. Wait, D0 is 1 and 2. Oh yeah, I thought it was 0 and 1. Okay. So that's the first buffer is being loaded. Okay, that's good. And then 4 would be our, okay, we're gonna do something 4 times. Oh yeah. Makes sense, because we're gonna do 4 copies, individual copies, and we're going to do it backwards, I'm assuming. That's why we added 7. So we're going to do C3, 4E, 4D. So we're just flipping around, I'm assuming. Right. So we're doing this 4 times, but we are pushing that away. So we're going to do two nested loops, right? One of 8 bytes and one of 4 for all 4 chunks of 8. Okay. Right. So then we're pushing that away. We're loading our counter to 8, of course. We're loading DE into A. Well, we're doing a comparison here. That's fine. That's just boundary checking, right? Yeah, and then we're jumping. We're adding 22 hex to A. Okay, okay, so we're adding 22 hex to the byte, though. Okay, sure. And then we're doing another jump here. If that is if that's goes over the limit. So if the carry flag is not set, and we're writing that into the first byte E1 F7. Oh, so we're overwriting our own byte here. E1D0, wait, no, oh, no, E1D0, no, it was indeed correct, no. So we're adding, wait, let me check if that's correct. So C3 plus 22 is E5, yes. Okay. But we're doing something special if it overflows though, so then that's a different condition. So we're increasing HL now. So we're going to do E1D1. Okay, so we're just pointing here now, that's fine. And we're decrementing the E, right? So we're going backwards here in this one. And then we are back. So we're looping now, okay? We're getting E1 F6, which is indeed the next byte here, 4E. I'm comparing it with BC though. BC, that's 188, that's so weird. Okay, so that's, okay, fine. Oh, no, yeah, it is comparing to the hard, it's not BC register, right? It's the literal value BC, as in hex BC. Yeah, this isn't the register. Yeah, okay. So for some reason we are checking whether it's smaller or bigger than 188, and then if it overflows, we jump to 5B53. Otherwise, we add 22. Okay. Okay. So there's a couple conditions here on what manipulation we do on this byte based on these things here. So we're first comparing it with 188, and then if that's the case, then like if it's larger or smaller than 188, we just copy the byte as is. Then we add 22 hex, and then again we check over it if it overflows, and oh, and we do add 188 again here. So that's a sort of like threshold. Like okay, sure. That might literally be an offset within the pattern table here. Yeah, okay. So that's not super relevant. We just have to make it so it's the exact same result, right? So what I assume is it's going to do all these bytes with these little comparisons and manipulations, and then we do the next one. Yeah, we add 8 to DE and loop again. We do that 4 times. Okay, so it's as simple as that. So where do we find this? Yeah, so this has to check the top bit though, and I think we're not doing that in the same position here. So we do that in dump temp buffer because we have to take 7F from the top. No, where did we do that? 7F. Yeah, it's in this function. Okay, so it's from this. It's in this variable. Okay. So and OXF0 80, I think, yeah, 80, right, equals OX80. So if the top bit is set, then we have to mirror the temp buffer. have a, it's not exactly a mirror, of course, because it's doing other, well, maybe it is, I'm not sure. But yeah, so we're going to do the same as in the game, right? So we're going to do the first, let's use ing, it's fine. Equals size ti equals 0. So we're doing this 4 times, and then we are doing the same thing 8 times. Oops. Actually, let me do that the other way around then. 7, so I can just index, right? Well, no, because I need to do it the other way around anyway. I have to, no, that's fine, that's fine. We have to do it 8 times. Okay. So when we're doing it 32 times, and then the mirrored temp buffer of a specific index equals the temp buffer of a specific index. Wait, but we have to check the values though. So first we do a comparison to hex BC. Let's first get the value. First get that value. So what's the index here? So I times 8 plus j, because that's it's 8 minus j or 7 minus j. What is it? Yeah, 7 minus j, right? Because we have to invert, we have to loop the temp buffer from the back to the front. So we have to, if j is 0, we do 7 minus 0 is 7, so we have from 0 to, that's 0 based, so yeah, that should be correct. And then the value or the position in the mirror temp buffer is simply I times 8 plus j, because that's from front to back, right? And then we have to do some comparisons. If current value, I think, what is this going to be? We're comparing it with BC, that was, and we're checking the carry flag. So I think if it's bigger than XBC, if it's bigger than, I mean, it might be smaller than, I'm not sure about that, but that's, I mean, that doesn't really matter. We jump to 5B53, which actually puts it in the thing. Okay, but then we do nothing. Okay, so let's swap it around. And if it's smaller than BC, we are adding 22 hex. And then if that has overflown, then we are adding BC again. I think. It might be easier to work with 16-bit values here though, to make sure that it's, then I can simply say if it's bigger than FF. I mean, I'm not sure here. Because we're adding BC, no, it should, no, I can't do it. I think I have to rely on the fact that this C++ code is going to behave the same way as the assembler here, but how can I check whether it overflowed though? Because they are checking the carry flag, but I can't really do that, right? Okay, let me see if I can find the value, and then we can calculate, right? So we're looping, we're loading a 4D, that's our next one. So 4D and BC, let's do that in decimal. 4D is 77, and BC is of course 177, I think. No, 188. So BC equals 188. So we have 77 and 188, and we're comparing the two, and the result is going to be put in the A register, right? No, it's just the flags that get affected. And the carry flag is set. So okay, are we crashing here? Am I still okay, Firefox is dead, I think. Yep. Are you coming back? No, apparently not. So we're comparing with a hard-coded value. So subtracts D from A. Yeah, so that means it's 77 minus 188, and then the carry flag is set if it goes below 0, right? Yeah. I'm assuming, right? That makes sense. So it's 77 minus 188. If that is less than 0, is that correct? Yes. And what is the condition? The jump condition is if the carry flag is set. So if that is the case, then we add the value by itself. Meaning if the value is lower than BC, I think, right? So if the value is lower than BC, we just copy the byte. And if it is bigger than BC, we add 22. So let's assume it is bigger. So let's say it's 190 is larger than 188. Well, yeah. Then we do 190 plus hex 22, which is what? Is 34. And if it overflows then in the other direction, then we add BC again. Which would flip the, well, no, because I'm using an unsigned thing here. Okay, do we have a byte where it's not, where that is the case though? So this one just writes. Now we have E5. Okay, now we don't jump. So E5 is one of these guys that matches. E5 is 229. That makes sense. 229 is larger than 188. So that's already correct then. So we're adding 22 hex. That makes it 263. Okay, so 263 is larger than 255. So I'm thinking the carrier flag is going to be set now. Right, so we have E5 plus 22 hex becomes 07, and the carry flag is set, right? So we have to add that thing again. Okay, so now wait, let me think. How can we detect that the jump was? Well, if it is smaller than the starting value, right? If current value is smaller than the original value, that would make that would mean that it would have flipped, right? Yeah, that's the only way that can happen, I think. equals smaller than this, then we add BC again. Right, because you do like a thing, if this overflows, that would make it, and it's an unsigned, right? It's an unsigned, so it just starts at, it goes from 255 to 0 again, making that value smaller than the original value. So let's just call this original value, and then also current value is original value, and then I don't have to index again here. Right, I think that is correct, not sure though. And that gets written out to the thing here. And now the question is, do I simply copy from the mirrored buffer? I think so, right? Because, okay, so let's see. So we have 7 now, and we add BC to 7. Which is indeed C3, which is 195. Wait, so we started with E5, right? Did we start with E5? Yes, we started with E5, which is 229. 229 is larger than 188, so we did 229 plus 22, well, 34, I guess. Yeah, plus hex 22 was 263 equals hex, well, 263, that's correct, right? Yes. And then that's larger than the limit, so we subtract FF, meaning, well, I mean, it's going to be 7, right? Because the result was 7. And that's smaller than the original. Yeah, I think that's correct. Yeah, the question now is, we just copy from the mirrored buffer. Is it as simple as that, right? So I'm gonna have to escape this function because we figured this one out. Assuming it's this one. Yeah, so yeah, now we have our copy routine, and the copy routine didn't change, and DE is just pointed to a different buffer. That's it. Yes, so I think we can now, I mean, we have to check the top bit in our copy function as well, but that should be fine too. Actually, we can yeah, we have to do that here, write them buffer. Should mirror equals this. Okay, and then, oops, and then this one should get a yep, and then we need a standard array pointer. No, that's the output buffer. 32. And then we have to use it, of course. What's wrong? Buffer. All right, we have to can we do that, I guess. Okay, let's see if it changes something. Right, so we have E3 for D, and we're outputting E5 for E, and that's exactly what we needed, right? I think it works. And we have our BE and BF. That might not be entirely correct though. And let's see what the end results gives us. So at least we have. I mean, I should output both buffers though. Wait, where do we do this? Yeah, dump 10 buffer should be. Yeah, let's do it like this. And then also 10 buffer to use mirrored, and then let's give this one 10 buffer to use regular, and then we'll do the same thing here. So we're dumping the correct buffer. Let me get that code here copied. Okay, so we have temp buffer to use, temp buffer to use, and then we can just use buffer. Okay, then we're dumping the correct buffer in our output here as well. What are you complaining about now? Oh, did I not do an asterisk? I don't think I did. Okay. So yeah, now we're outputting our mirrored buffer as well. Okay, let's look at the output here. So we have BF. Yeah, it is BE, BF, BE, as in BE, BF, BE. So that should be fine here. So we have the first chunk, and then this guy here, right? E5 for E. Yeah. So let's now see how the entire thing, or at least the first two rows, look like. Yep. Okay. So we're comparing this. Okay, we made a mistake here because something is being nulled here. That sucks. But let's look at our bottom part. So we have E3 for D for E, yeah, that's correct. And then E5 for D for E. And then again, E5 for E. We stop with C1. Did I do one? Did I stop too early? Why is 0 only the two top ones? And from, oh yeah, I mean, that would be better. Right. And then the last one is E3 for D. Right. So and now we have BE E0, BF E1, C8 59. Yep, that's also correct. And then we have a BE E0. We have an E0, E1, E0. Yep, this one, and this one. Yeah, so that's all correct. Oh yeah, I didn't do the fourth one. That's why it was zeros. So this is completely correct now. So we've decoded the top two rows of the entire width. So that's good. Let's see if we fail at one of the following ones then. So let's do another row. I might need to print out more though. Yeah, I need to print out more. Dump output buffer doesn't print enough. So 256, that's going to be 512 then, right? If we have to double it. So what we have 4. Wait, 1, 2, 3, 4, 5, 6, 7, 8, of course. And then 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. So we need at least it's more than double though. It's 512 is not going to be enough because we have 5 rows. So we need 32. No, 4 times 32. Okay, so we have 32 bytes per row, and we have 20 rows. Yeah, I think we have 20 rows. That's 640. Is that? Yeah, I think it's 640. Is it total? The total screen. Okay, it's not correct. Well, no. We're only outputting. Right. We're only outputting the first 3 rows. So that's why it's all zeros here. But what we added now is the chunk below here, right? So this chunk here. So let's see what it looks like. I'm gonna let it run, and then we can compare everything except the bottom chunk or bottom 2 chunks, 2 rows of chunks, which is solid data anyway, but fine. So we might as well do that as well. C7, E9 I see, and then here it starts again, E1, BD, 40, 40, 40, 40. Okay, this is wrong, but sure. And then 40, 40, DF, BD, 40, 40, 40, yep. E2, 40 for C, yep, that's also correct. E5, no, that's incorrect, I think. Well, we have E5 for D, but we're missing some stuff here. Okay, so we're missing a couple bytes. Then we have E5 for E5, 3 for C for D, 4D for C, 5, 3. Yeah, that's also correct. Then we have E0, 54. We're missing stuff here. And we have wrong data here, sure. And then I think that's the bottom, well, no, the bottom rows are here, right? That's the 5E, 5F, and that's the adornments. So we're missing some stuff. But I'm assuming that we're going to encounter the 20 hex. Yeah. See, we have the 20 hex now and the 10 hex too, and we haven't implemented those at all. That makes sense that it's the wrong data, of course. Yeah. So now we just have to implement those cases, and then I'm assuming we are going to get better output for the missing ones here and the incorrect ones. Yeah. So considering the pointer of the room starts here, that's also interesting because it contains lots of moving data. So the tile indexes are here, and the pattern tables, I mean, those are, or the name table, those are like static, of course, but we see lots of stuff happening here. That's also interesting to know if there's something we can mess with. I mean, clearly that's the blinky thing. Yeah, not sure what it all does, but like if we mess with these values, nothing really changes. I mean, they get overwritten immediately, of course. Now, I mean, if you change the wrong one, then it doesn't really like it, it seems, which is fine. Oh, and it's completely resetting now. Game over and reset the console. Okay, that's fine. Right, so let's have a quick look at how the other routines look like. And I have to find them again. I didn't write the address again down again, so I'm not sure where that is. I'm talking about these guys here, these two, right? The 10 and the 20 hex that we have to do. So let's see. That was this one, I think 59E7 perhaps. Wait, let me clear all the breakpoints here. Oh no, I can go there, right? It's this one, decode level data temp buffer. Yeah, it's this guy here. So in case it's 10, we have 5A32. That's this. Wait, let me look at it here. Yeah, so these are the guys. And then 5832, what does that do? We have a return here. Okay, that looks like a little routine that does the exact same thing at the end here, loading the pointer again. 5808, that jumps back to oh yeah, no, that is included in this function. Okay, and 5829 is the other one. So only for 30 does it jump like way out of this function at 5843. Oh no, 5843 is here. Okay, no, the function runs here. So all three of them are on top of each other. Yeah, so this is the 21, then above that we have the 10, and this is the 30. Okay, that does make sense. Yeah, and then at the bottom we just return, and we have the so we're loading 40 hex. That's a weird number, and then oh wait, no, we're jumping to 5838. Okay, that's a bit weird. Why we're skipping this 5836? Do we do that somewhere? No, but that's fine. So we have 40 in the C register, and we're loading the byte, taking the bottom nibble, putting that into B. Oh, and we're writing 40 hex into the thing. Okay, so it's a simple repetition count that does 40 hex instead of 0. But surely 5A36 is being used because we're doing this, right? We are writing 0 n times. Yeah, that's this. That's the fall through, or the top nibble being 0. Wait. That's at the top here. Yeah, 5836 is being jumped from here. So that jumps here. So it's the exact same thing, except with a value of 40 instead of 0. Okay. Right. So yes, and that is the 10 variant, right? We jumped to 5832. Yes, that's the 10 variant. So that's super simple. That is this one. And instead it's 40 hex. Okay, I mean, let's look at the other one too then. The 21 is 5829. That's this one. And that jumps at 5A3C, which writes C into, oh, that's a custom value then, right? Do we populate? Yeah, we populate C here. So we have a version for 0, for 40, and I think this one is custom. So we're loading the byte, we're taking the bottom nibble, putting that into B. We're going to the next byte, putting that into A, and putting A into C. Okay, so okay. B might be a counter then. Is B a counter? Because we're jumping to 583C, and we're loading C into HL, incrementing HL. Yes, because that's the loop. 583C is being looped. So the counter is in the bottom nibble of the first byte, and the value is in the second byte. Okay, so we have to have bottom nibble, and that's our counter. Bottom nibble is this. Still confused why this doesn't work though. Let's try that again. So we would say this equals bottom nibble equals meta and OXOF. So why does this not want to compile though? Yeah, that's just unused. Now it's unused. Okay. What did we say? So that's the loop count. And then the value equals this. Right. Do we do our incrementing at the bottom? No, right? Yeah, we don't. So that's good, because we do have to go to the next one, and then we just do the same thing. So that's a loop with the loop counter determined by the value, by the thing. Oh no, that's the exact same thing. Wait. Yeah, that's the exact same thing. It's just a value that changes. The loop counter was already a thing here. Okay, sure. It's the value that changes here. Yeah. All right. If it's that simple, then let's try and see if it's better now. I have to go back to the correct thing here because that's playing on its own here. Wait, I need to see where to break. So not in this function, but above this function, because I want to see the entire array now. So I'm going to have to go up from this one. Yeah, and even up from this one, right? Because this is called per chunk, right? So up from this one. Yeah, this does it 4 times. And 14 is 16 and 4 is 20. So yeah, this does it 20 times. So pretty much we have to stop after this for loop here. I think then it will be completely loaded. Yeah, this one here. So let's compare. So we have our 5 Fs and 5 Es, E3, E5, yeah. Then E0, E1, E0, that's correct. We have this one too. C7, E9. Okay, and it went wrong here, right? E1, BD40s, BC40. Okay, so that's wrong. BC is still wrong. And then we have 40s. That has nothing to do with our 10 and 20. Well, maybe it does. It could be. Then we have 40DF. That's correct. We have BD40s. Yep. E2. 4D, 4C, 5, 3, 4E, C3, E5, 4E, 4D, C3, EF, E5, 4E, 4D, C3, yep. Then E5, 4E, yeah, that all looks correct though. 4D, 4C, 5, 3, 4E, C1. This is incorrect. Wait, am I on the right line here? No, I'm not, that's correct. 54. I'm gonna add some more here, make it complete by doing 5 rows. Yeah, we see the bottom wall as well here. Yeah, we only encountered one mistake here. That's weird. And then so E0, E1, E0 again. Yeah, we have these guys, the 54s. Yeah, 54BF. Yeah, and then the 54 here, BE, E4, and then a bunch of 40s, 41, 40, 40, BC, 40DE, 40, 40, 40, yep, that's all correct, 40, 40, 41, 40s, 41, 40, C2. Okay, is there only one error in there? And it was, which one was it? Is DE. At BC40, yeah, this guy, one mistake. All right. I mean, it is a bit weird that there's just simply one mistake in there still, but fine, I guess. We'll have to figure that out next time. Yeah, but once we fix that, next thing we'll do is figure out the tile data itself. So we'll get the composition of all these sprites or all these tiles. So we have the tile sets and the color sets. So we have to extract those. And then we can combine that information with this, and then we'll render a PNG with the first thing here, right? With this, like this PNG that here we should find and like decode, and then write a nice PNG with that information. All right, but that's going to be it for now. Thank you all for watching, and I hope to see you next time. I think it will be, what is it, Wednesday? No, it's Thursday, probably on Saturday. So I hope to see you then. Bye.